Donc, on est de retour et on est très content de vous voir. Pour les nouveaux, je suis Luc Vinet, je suis le directeur d'Ivado. Ivado est un grand institut financé par le programme Apogée qui a la mission dans un projet très ambitieux qu'on appelle IAR3, de faire avancer la science de l'IA et son adoption, et ça de manière responsable. Et dans ce programme qu'on embrasse, on a aussi, si on veut être responsable, c'est responsable d'intégrer les dimensions quantiques, ce qu'on entreprend avec ce séminaire. So I'll now switch to English to make it easier for our speaker to understand what I'm saying. So welcome. It's great to see you all at this reprise of the Ivado Quantum seminars. And we will start with youth, this, fall series with NickOrmrod, who's coming from the perimeter where I was actually no later than last evening. The perimeter is celebrating its 25th anniversary, and Nick is a postdoc there in the group on the foundation of quantum mechanics. And he's done his doctorates, DPhil, I suppose it is, at Oxford, with having done previously a master's in Bristol, at the University of Bristol, so my informations are correct. And he will tell us, I'm sure it will be a fascinating talk. He will talk to us about causality, basically. And his title is right there, The History of Decoherence and New Horizons. So Nick, if you would please.
All right. Well, thank you very much for the introduction, and thanks for having me to speak to you today. Yeah, it's a pleasure to be here and talking about decoherence and causation and the interface between them. In this talk, I'm going to be talking about both the history of decoherence and what I think its future might look like. And I'm going to be coming at things very much from this perspective shaped by recent advances in quantum causal structure and generalizing the framework of causal modeling to quantum theory. So far, there hasn't been a lot of traffic between the fields of decoherence theory and the fields of quantum causal structure. But I really believe that those two fields are deeply intertwined and that each one really requires the other in order to advance forward. So that's what this talk is about. And my main thesis is that traditionally decoherence has been held back by the state-first view of physics, on which states are more conceptually fundamental than dynamics, right? So typically, the way that people think about dynamics is just as a kind of rule that tells you how the state is going to change over time. They have no intrinsic significance. Their significance is cashed out only in terms of their implications for states. And I think that's the view of physics that's been holding back decoherence. But today, the notion of quantum causation actually enables us to formalize a dynamics-first view of decoherence, resolving key problems and even, at the end of the day, leading towards a novel realist interpretation of quantum theory. So it's a thesis that divides into two parts, and as a result, the talk is going to divide into two parts. In the beginning, I'm going to be talking mostly about these historical claims about decoherence in the state-first view. And then I'm going to go on to tell you about new stuff, how we can, well, first of all, what we mean by a quantum causal influence in the first place, and then ultimately how we can use that concept and the related mathematical formalisms in order to pin down this radical reimagining of the concept of decoherence. And I'm going to tell you about the payoffs of doing so as well. Okay, now in this first historical part of the talk, clearly in a talk of this length, I don't have time to give you an extensive introduction to everything that's happened in the history of decoherence. So instead, what we're going to do is we're going to zoom in on the work of one particular physicist, Wojtek Zurek. Now, Zurek is a very natural choice to make, to focus on, because not only was he a pioneer of decoherence theory, but he really remains to this day one of its most influential contributors. So by putting his ideas under the microscope, we really learn a lot about how people more generally think about decoherence. Okay. Now let me start by giving you a little bit of an overview of what I'm going to be claiming about Zurek's early work on decoherence. The key point is about a tension in Zurek's work concerning the role of the dynamics. So in particular, Zurek identifies as early as 1981, which is really his first paper on decoherence, that the dynamics are mathematically primary. So what do I mean by dynamics being mathematically primary? What I mean is that the chief purpose of decoherence is to help us identify certain preferred and effectively classical degrees of freedom, or observables. But that's done by the dynamics alone. Zurek notes explicitly that all you need to know is the Hamiltonian in order to figure out what degrees of freedom are preferred according to decoherence. So they play this kind of structurally or mathematically primary role. But at the same time, in the story that Zurek tells about decoherence, dynamics actually play a conceptually secondary role. And the primary role is played by quantum states. So that's the tension in Zurek's work. It's between the mathematically primary but the conceptually secondary role of dynamics. And the reason why this tension exists is because Zurek is following the kind of state-first view of physics according to which dynamics are always conceptually secondary in the way that I just described a moment ago. That is, dynamics are always thought of as just rules governing the evolution of quantum states. Ultimately, I'm going to be advocating in the second part of the talk a way of escaping this state-first view of physics that enables us to pin down a dynamics-first account of decoherence. Good, so we're going to begin our examination of Zurek's work by looking at this landmark paper on decoherence. It's a very highly cited and highly influential paper in the field. And in this paper, he tells a story that many of you will probably recognize because it's become really one of the most famous stories in quantum foundations. And it's the story of how you solve something called the preferred basis problem. Okay, so what is this preferred basis problem that Zurek is intending to solve with this paper? Well, the preferred basis problem is essentially a challenge for the view that all time evolution is ultimately unitary. So if all time evolution is unitary, then that means that in particular, a measurement that we perform has to ultimately be treatable as a unitary interaction. So that means we must be able to give adequate unitary models of measurement. There must be a mathematical model that we can write down where we look at that model and we say, yeah, we can understand that as representing a measurement taking place. But the preferred basis problem raises a challenge for that. And the challenge is that unitary models of measurements produce states that fail to determine the measured basis. That's the one sentence version. Unitary models of measurements produce states that fail to determine the measured basis. But now let's see how that works in more detail. So in setting up this problem, I'm going to stick pretty close to Zurek's exposition in that 1981 paper. But I'm going to simplify things as much as it's possible to simplify them. We're going to model both our system and the apparatus that we're going to use to measure the system as the simplest kind of quantum system, which is a qubit. Right, so two-dimensional Hilbert spaces, each one of them. And the aim of the game here is we want a model of a measurement of this particular basis for the system that I've labeled 0 and 1. In order to attempt to measure that basis, we're going to couple together the system and the apparatus using this Hamiltonian. In that expression, in the top line expression for the Hamiltonian, I is the identity operator and X and Z are the usual Pauli operators. And so the eigenstates of the Z operator are that basis that we want to measure. Good. Now, when we run this Hamiltonian for a particular time, we notice that it ends up generating this evolution of states. So here I've got an arbitrary superposition state for the system, because I don't want to assume anything about the state of the system. That's what we're trying to measure. But I'm assuming that the apparatus starts in the sort of definite ready state that I've called 0. And when we run the Hamiltonian for the right amount of time, we see that eventually we get this correlated state of the system and the apparatus. The system and the apparatus are perfectly correlated in the 0-1 basis. And so you might look at that state and say, well, hooray, we've done it, right? We've carried out the measurement, because a measurement is just about making the thing that we want to measure get correlated with the apparatus that we're using to measure it. And there is that correlation, and it's a perfect correlation. But actually, the only reason why things look so good is because I have chosen to decompose the state psi in a particular basis. But really, yeah? Yeah, that's a good point. So for most values of the coefficient, for most values of the coefficients A and B, the Schmid decomposition of the state will be unique, and it will be that decomposition. That's true. But part of the problem is that sometimes for certain values of A and B, the Schmidt decomposition is not unique. And even when the Schmidt decomposition is unique, there's an only slightly milder version of the problem that still arises. So let me start by explaining the problem when the Schmidt decomposition is not unique. So that happens when you've got these particular values for the coefficients. A is 1/√2 and B is I/√2. In that case, you've got this non-unique Schmidt decomposition where you can write psi in either one of these two ways, right? And then the essence of the preferred basis problem is this. If the top line implies that we have measured the 0-1 basis, then by exactly the same argument, the bottom line must imply that we've measured the plus-minus basis, right? Because these two decompositions are identical. And so it's true, to bring it back to that question, we only get this particularly acute version of the problem in this kind of fine-tuned case where we have a truly non-unique Schmidt decomposition. But suppose I just perturb the values of the coefficients slightly, then our conclusion would only be slightly different, right? We'd still have perfect correlation in the 0-1 basis, and like almost perfect correlation in the plus-minus basis. And so we'd still be left wondering, what, if any, justification do we have for regarding 0-1 as the basis that got measured and plus-minus as a basis that did not get measured? Essentially, the preferred basis problem boils down to a symmetry that we don't want, right? There's this symmetry of the state here where it looks invariant with respect to these two different bases, and it means that we can't regard either one as being preferred over the other. The state alone doesn't give us any justification for regarding any one of the bases as measured to the exclusion of the other one. So this is the preferred basis problem as Zurek sets it up. Now, how does he go about solving this problem? Well, according to Zurek, the root of this problem is an unrealistic assumption that we've made. Because in order for the system and the apparatus, just the two of them, to be evolving unitarily, we have to assume that they are perfectly isolated from their environment. Now, if the system is just like the spin of an electron, then we might think that we're able to contrive a situation in which it's pretty well isolated. But we're making it interact with an apparatus. And if it's an apparatus that we can actually read, then it's going to be a macroscopic apparatus. And macroscopic apparatuses interact with their environment. It's effectively impossible to prevent that. And moreover, even if you could prevent it, you wouldn't want to do that, right? What is an apparatus? It's something that you look at and it tells you what the outcome of the measurement is. But you can only look at things which are interacting with the electromagnetic field that, mediates your vision, right? So it's an assumption that's both unrealistic and undesirable. Yeah. Mm-hmm. Mm-hmm. That's right. That's right. But but what Zurek is going to argue is that the particular kind of entangled state that you end up with is less problematic than that one, because it doesn't have the same problematic symmetry. So we can see this now. Keeping things really, really idealized and really, really simple. I'm hoping you'll let me get away with just modeling the environment as another qubit. And then we can couple the apparatus and the environment using this Hamiltonian, which has the same form as the Hamiltonian that couples the system and the apparatus. And Zurek argues that actually, apart from the fact that all of this is so idealized, this is actually a reasonable sort of Hamiltonian to expect governing the apparatus and the environment. Now, if we let this Hamiltonian dictate the evolution, then we see that it can give rise to this evolution. So here, for the system and apparatus, I'm starting with that problematic state, psi SA, that we saw a minute ago, and this sort of definite zero state of the environment. And we're ending up with this state that I've called phi. Now, this is another entangled state, but it's an entangled state that is different in a way that matters for the preferred basis problem, because it doesn't have the same kind of symmetry. And in particular, one way of seeing that is to trace out the environment in order to obtain a reduced density operator for the system and the apparatus. So I've written it there, both in Braun, ket form, and in matrix form. And it's clear from this state that the 0-1 basis on the system that we wanted to measure is still perfectly correlated with the 0-1 basis on the apparatus. That's good. But now it's the only basis on the system that is perfectly correlated with the apparatus. If you look at the matrix form of it, you see that these off-diagonal terms are all zero. And if you think about it, what that tells you is that 0-1 is the unique basis in which the system is perfectly correlated to the apparatus. It also tells you that there's no correlation whatsoever anymore with the plus-minus basis. Right? The way the correlations work is only the 0-1 basis is perfectly correlated from the apparatus, and as you sort of move further away from that basis in the block sphere, you get less and less correlated. And so, unlike the pure state that we saw before, psi SA, rho SA does designate the 0-1 basis as being preferred. And so we can reasonably use the state rho SA to argue that we have carried out a measurement of the 0-1 basis. Okay. So I imagine that many of you will recognize that story. It's certainly a story that gets told a lot in quantum foundations. Because although it was introduced in that 1981 paper, it's really become very influential. But what has become less well known from this paper is the insight that Zurek opens the paper with, right? And so far, I haven't mentioned this in our discussion. So this story that I've told is a sort of simplified version of the story that Zurek tells in the main body of the paper. But if you look at the abstract, Zurek is not focusing on correlations in states and problematic symmetries of states. He's focusing more on the dynamics. Oh, whoops, I guess I already said this. So he opens his paper with this. The form of the interaction Hamiltonian between the apparatus and its environment is sufficient to determine which of the measured quantum system can be considered recorded by the apparatus. So what Zurek says in that first sentence of the paper is that the dynamics in some sense are all you need in order to figure out which observables are marked out as being preferred or special by decoherence. And in the second sentence, he tells us how this works. So the basis that contains this record, the pointer basis of the apparatus, consists of the eigenvectors of the operator, which commutes with the apparatus environment interaction Hamiltonian. So if you want to figure out the preferred observables, it's all in the dynamics, and in particular, it's in the commutation properties of the interaction Hamiltonian, according to Zurek. We can see how this works in our particular example. So remember, this was the Hamiltonian that coupled apparatus and environment. The interaction term is the one on the right, and it's very easy to check that apparatus observables commute with that interaction term if and only if they are diagonal with respect to that 0, 1 basis. So given what Zurek just said in that abstract, it follows that 0, 1 is the pointer basis. And we were able to figure that out very quickly just by looking at the Hamiltonian alone. We didn't have to look at states. And so it raises this question. Given that Zurek has this insight that the dynamics alone determine preferred observables, and he even thinks that this insight is so important that he puts it in the first sentence of the paper, why the emphasis on quantum states in the story that he tells about decoherence? This is an instance of this tension that I mentioned in Zurek's work earlier. The Hamiltonian alone determines the preferred basis, yet Zurek appeals to states in order to explain why the basis is preferred. Now, this tension makes sense. We can understand why it comes about. We can understand why Zurek did want to talk a lot about states in the paper. Because Zurek is following the state-first view of physics. And again, according to the state-first view of physics, dynamics are nothing except rules governing the evolution of quantum states. And Zurek doesn't just want to give you a mathematical criterion like commutation with the interaction Hamiltonian that allows you to just identify one basis that is marked out. Zurek wants to do more than that. He wants to give you a conceptual justification for regarding a basis as preferred, and ultimately for regarding a particular basis as being the measured basis. And so the way he's giving you that justification is he's telling you what the Hamiltonian does to the evolution of states. For Zurek, the reason why commutation with the interaction Hamiltonian matters is because that's what allows the pointer basis to be unchanged by the interaction with the environment. And that's why it's only correlations with the pointer basis of the apparatus that can survive the interaction, right? And that's why the basis ends up being preferred. So we can understand why dynamics are playing a mathematically primary but conceptually secondary role here. It's just downstream of the conceptually secondary role that dynamics always play on the state-first view of physics. If we want a view of decoherence where dynamics play a conceptually as well as a mathematically primary role, then we would need an alternative to the state-first view of physics. Okay. Now I'm going to develop this theme of this kind of tension in Zurek's work further by talking about some other of his work from the early 90s, but some essential background for this next bit is about the consistent histories approach to quantum theory. So this is a formalism that was first introduced by Robert Griffiths in a 1984 paper, and it was developed further by Gell-Mann and Hartle later on. And I can tell you some of the core ideas of this consistent histories approach to quantum mechanics. So to begin with, just consider a time-ordered sequence of PVMs, right? So each PVM, it can be thought of as representing a measurement, but mathematically what it is it's a set of projectors that are orthogonal to each other and sum to the identity. And we have a time-ordered sequence of them. So the projectors P1, they happen at time 1, et cetera, et cetera, et cetera. Now, I'm also assuming here that we are representing each PVM in the Heisenberg picture. And what that means is if there's any unitary evolution that takes place between the PVMs, then we're just going to absorb that unitary evolution into the definition of the projectors in the PVM. So that means that our PVMs are taking into account the unitary evolution as well as the measurements themselves. Okay. Now, in a pretty straightforward way, any time-ordered sequence of PVMs induces a history set, where every history in the history set is a time-ordered sequence of projectors where one is taken from each of the PVMs that we started from. For any history set, we can always define a probability distribution. We start with some initial state rho, and we just kind of iteratively sandwich rho between projectors associated with increasing time. It will always define a probability distribution. But that probability distribution might violate the sum rule. So what does that mean for a probability distribution to violate the sum rule? Well, what it means is we could take the PVMs that we started with and we could coarse grain them, right? You can coarse grain a PVM by summing together some of the different projectors. And after you've summed together certain projectors, what you're left with is a PVM with fewer projectors, which project onto larger subspaces of the Hilbert space. So it represents a more coarse-grained version of the measurement that you started with. So imagine that we coarse-grain some or all of these PVMs that we started with, and then that gives rise to a coarse-grained history set, and that gives rise to, oh, whoops. Sorry about that. Somehow went back a long way. Okay, so we have a coarse-grained sequence of PVMs, coarse-grained history set, and then we can have a probability distribution over the coarse-grained histories. It can sometimes happen that the probability of a coarse-grained history is not equal to the sum of all the probabilities of the corresponding fine-grained histories. And that's what I mean when I say that a history set can violate the sum rule. We call history sets that violate the sum rule inconsistent. And the history sets that happen to respect the sum rule, and there are some of those, are called consistent sets of histories. Yeah. No. So that's sufficient but not necessary. Yeah. So if your PVMs all commute, then indeed they will always form a consistent set of histories. But another case in which you get commutation would be, say, you had like 2 PVMs. Well, actually, anytime you only have 2 PVMs, then you'll get a consistent set of histories. Yeah, it can happen for other reasons other than commutation. Okay. So yeah, so consistent set of histories is one that satisfies the sum rule. And Robert Griffiths in the 1984 paper, he laid down something which we can understand as a necessary and sufficient condition for consistency. So what do we make of this expression? Well, this thing that we're tracing, it can sort of be understood as representing the interference between the unprimed and the prime history, right? And then we're taking the real part of that interference term. So the consistency condition is kind of demanding that the real part of the interference between different histories goes to 0. That is necessary and sufficient for the sum rule to be satisfied. And given that we can intuitively understand it in terms of the vanishing of these interference terms, it's not surprising that people make a connection between consistent histories and decoherence. Indeed, in the version of the formalism that Gelman and Hartle developed, they actually called the framework decoherent histories. But as we're going to see in a second, Zurek has some things to say about the exact relationship between decoherence and consistent histories. Okay, so now I can get on to this next work of Zurek's that I want to talk about. This is a publication that is based on a talk that Zurek gave at a conference with a number of experts on decoherence, a conference in the early 90s, and there are various different versions of this publication floating around. But in this particular version, you find at the end a transcript of some of the discussion at that conference. So we're going to be referring both to Zurek's talk and the transcript of the discussion. Now, one of the things that Zurek is doing in this paper is he's taking issue with the way that many of his colleagues think about decoherence. And in particular, he's objecting to what he sees as bad definitions of decoherence. He thinks that many of his colleagues are guilty of, as he says, mistaking symptoms of decoherence for causes of decoherence. And an example of that is diagonality. So diagonality came up in our discussion of decoherence before. Remember, I gave you this matrix and I used it to argue that 0, 1 was the unique basis for the system perfectly correlated with the apparatus. Decoherence plays a, the suppression of off-diagonal terms, or diagonality, it plays a role in the story, in Zurek's story of decoherence. And as a result of that, many people have taken diagonality to actually give you a definition of decoherence. It's probably, at least among people who aren't experts on decoherence or focused on decoherence, it might be the most common definition of decoherence you actually hear. You ask somebody what's decoherence, they'll often say, oh, it's the suppression of off-diagonal terms in a density matrix. But Zurek, who was so important in establishing the field of decoherence in the first place, actually really rails against that understanding of decoherence. He doesn't like it at all. And here's what he says about it at the beginning of that paper. It'll be pointed out that diagonality alone is only a symptom, not a cause, of the effective classicality of the preferred states. And as all symptoms, it has to be used with caution in diagnosing its origin. Causes of diagonality may on occasion differ from those relevant for the dynamics of the process of decoherence. So the point that Zurek is making here is pretty clear. He's happy to say that decoherence generally leads to diagonality. But he's also pointing out that diagonality is not sufficient for decoherence. You can have diagonality for other reasons. And he gives the example of ignorance of the observer being a reason why you might have diagonality without decoherence. But we could add another reason is you might have just started with a particular initial state, like a fine-tuned initial state that just happened to lead to a diagonal density matrix at some point. It's not always the consequence of the kind of interaction Hamiltonians that Zurek identifies as being responsible for decoherence, right? Good. And this insistence on not mistaking symptoms for causes, we can view it as being quite closely connected with the way that Zurek chose to open that paper, right? The 1981 one, I mean. He opened that paper getting to the structural core of the issue, saying the interaction Hamiltonian alone suffices to determine the preferred basis. Zurek is very anxious not to mistake the sort of surface level symptoms of decoherence for its essence or its underlying causes. Good. Now he's going to make a similar argument against the use of consistent histories or decoherent histories to define decoherence. So he thinks that the term decoherent histories is kind of a misnomer. Consistency conditions alone are not as restrictive as the process of decoherence tends to be. They can be, for example, satisfied by violently non-classical histories, which obtain from evolving unitarily projection operators which initially diagonalize the density matrix. That's sort of like the consistent histories that you were talking about earlier. The relation between decoherence and consistency clearly requires further study. So Zurek's point here is that you can define these consistent sets of histories kind of on the cheap by just picking your favorite PVM to start with, and then just defining subsequent PVMs that are just sort of unitarily evolved versions of that first PVM. But you could do that for any PVM you like. And so clearly, this is not a case of decoherence selecting preferred degrees of freedom. So again, the argument against consistency is similar to his argument against diagonality. Maybe consistency is a symptom of decoherence, but it's not what is behind decoherence. Okay. So given that Zurek was making these points at this conference and criticizing a number of his colleagues working on decoherence, it's not surprising that some people in the discussion asked him, okay, well, what's your definition of decoherence? How would you prefer that we define it? And in that transcript, Zurek says something really, really interesting. I feel that the term decoherence is best reserved for the process which destroys quantum coherence when a system becomes correlated with other degrees of freedom. There's a lot going on in that quote. But I guess I would like to break it down into two halves. So that first half of it, I feel that the term decoherence is best reserved for the process. It sort of feels there like decoherence is gesturing towards a dynamical or maybe even dynamics first view of decoherence, the kind of thing that I've been advocating for, because he calls it a process. But in that discussion, Zurek doesn't give you a general, precise definition of what he means by a process. And in this particular quote, he's giving us no way of characterizing exactly what processes are responsible for decoherence, other than features of quantum states that the process ultimately leads to, right? He talks about destruction of quantum coherence, so that's diagonality, which is something that he's already argued is a symptom of decoherence rather than a cause. And I want to be a little bit provocative by going further than that and arguing that actually, even this thing, at the end of the quote, the correlations that Zurek talks about with other degrees of freedom, I think we could argue that that thing is also a symptom and not a cause of decoherence. Why? Because again, Zurek identified at the beginning of his 1981 paper that the form of the interaction Hamiltonian is all you need to determine the preferred observables. And if that's true, then that suggests that the causes of decoherence or the essence of decoherence or the definition of decoherence should be found purely within the unitary dynamics. We shouldn't have to appeal to the state level symptom of diagonality, but nor should we have to appeal to the state level symptom of correlations. So again, what I'm saying here is that I think we can kind of turn Zurek's own argument around and say, well, granted that we don't want to be guilty of mistaking symptoms of decoherence for causes, that means what we need is a truly dynamics first understanding of decoherence, and therefore we actually don't want to be doing what Zurek is doing here and still relying on features of quantum states in order to supply the definition. Okay. So that brings me to the end of this more historical part of the talk. Now what I'm going to try to do is put my money where my mouth is and actually articulate the alternative to the state first view of decoherence, to show you how we're able to articulate a dynamics first understanding of the concept using recent ideas in causal modeling. But I'll begin that with just a brief summary of how the field of causal modeling has developed. So to begin with, it has nothing to do with quantum theory, right? It has nothing to do with quantum theory. We can phrase the kind of problems that motivate causal modeling in a classical case. So suppose that A and B are some observed variables that you're collecting data on. And you collect your data, and in the long run, the data converges to that probability distribution in that table. Now, this probability distribution tells you some things. It tells you that A and B are perfectly correlated, but it doesn't tell you everything that you might want to know about A and B. It doesn't tell you, in particular, how they're going to respond when you perform interventions on them. So suppose, for example, that you intervene on the system and you just reset the value of A. So whatever it is, now you're going to set A equals to 0. Is that going to lead to the value of B being 0? Or will the value of B remain whatever it was before? Does an intervention on A change the statistics for B? Well, the correlated probability distribution doesn't tell you one way or the other, because you need to know the causal structure. If the reason that they're correlated is because there's a causal influence from A to B that forces B to take the same value that A does, then an intervention on A might lead to a change in B. But if the causal influence is in the other direction, then intervening on A can't make any difference to B at all. And if the correlation is as a result of a common cause, then intervening on either variable won't make any difference to the other one. So if you want to be able to talk about the consequences of interventions, you need to know about the causal structure. But if you want to know about the causal structure, you have to start by knowing what causation is in the first place. And this is what motivates the framework of causal modeling that was developed by Judea Pearl and was really sort of completed only a couple of decades ago. It's explained all in that big causality Bible. And the very basic idea at the heart of his causal modeling framework is the following. It's an account of what causal influence is. So if you want to say what causal influence is, you have to say in precise terms, what are the relata of causal relations? What are the things that exert influences and get influenced? And you also got to say what you think it means for them to exert a causal influence. And for Pearl, causal relata are variables. Variables influence each other. And what does it mean for them to influence each other? Well, one way of thinking about causation in Pearl's framework is you assume that there's an underlying deterministic dynamics that governs the evolution of all the variables in the world. And those deterministic dynamics can be represented by a collection of functions. And then you end up defining causal relations as functional dependencies. So a causal relation for Pearl is the value of one variable depending functionally on the value of another. Now that definition of causation gives Pearl a firm foundation to set up a whole causal modeling framework. So he has an extensive framework for making inferences between observed data and causal structure, predicting consequences of interventions, and even evaluating quite complicated counterfactual statements. Okay. And it's been a very, very influential framework, both in academia and in industry. It's been used in AI, machine learning, medical research, and companies like Google, Amazon, Spotify, they have dedicated teams working on these causal inference tools. So it's been a very, very successful framework for causal modeling that Pearl developed. But it doesn't work for everything. And in particular, it's very awkward when you try to apply Pearl's framework to explain quantum correlations. Doesn't naturally accommodate quantum phenomena, a particularly good example being non-local quantum correlations or Bell inequality violations. It's not that you can't provide a causal model of the Bell inequality violations, you can, but it's always really awkward and not entirely explanatorily satisfactory. So for one thing, in order to reproduce Bell inequality violations in Pearl's framework, you have to posit the existence of at least one hidden causal influence. Where by hidden, I mean that you can't exploit that causal influence for signaling. Now, you might think that it's just bad methodology to do that in general, but even if you're happy to do that, then there's another problem, which is that in order to prevent that causal influence from leading to the signaling that you never observe, you got to fine-tune the model. You got to fine-tune some probability distributions in order to wash out the possibility of signaling as a result of that causal influence. So it's kind of doubly awkward. And it's not really surprising that Pearl's framework can be quite awkward when applied to quantum theory, because it's given in the language of variables and functional dependencies and not the native quantum language of algebras of observables and unitary channels and so on. And that leads to an intriguing possibility. Given that Pearl's framework doesn't naturally extend to quantum theory, could it be that part of the core reason why quantum theory is so difficult to make sense of is that it rejects the very intuitive notion of causation that is captured by Pearl's causal modeling framework and replaces it with an alternative, exotic, counterintuitive quantum notion of causation? Could it be that this alternative quantum concept of causation is what lies behind the violation of Bell inequalities, but more generally lies behind many counterintuitive aspects of quantum theory? So a number of people in quantum foundations had this idea about a decade ago, and it inspired a huge amount of work seeing whether or not Pearl's framework and the notion of causal influence could be generalized or adapted to quantum theory. And there's a whole flurry of papers now on causal modeling frameworks in quantum theory. And as you can see, there's various different approaches by different authors. But what these frameworks provide, each in their own way, is a way of generalizing the basic notion of causation that you find in Pearl, and using that quantum notion of causation, developing generalizations of all of the core causal modeling tools that Judea-Pearl gives us, right? So at the heart of Pearl's framework are these ideas like the Markov condition, D-separation theorem, do calculus, counterfactuals. Doesn't really matter if you don't know what all these things are, but the point is they're just like the core tools of the framework around which everything else revolves. And you have those same core tools being adapted to quantum theory in these frameworks. So it turns out that although Pearl's framework of causal modeling doesn't work in quantum theory, there are causal modeling frameworks that work based on a different notion of causation. So this is good news. And at this point, it's appropriate to ask the question, can we get our heads around what's different about the quantum notion of causation that lies at the heart of frameworks for causal modeling? And can we use the notion of quantum causation to solve foundational problems? And in particular, to tie it back to what this talk is really about, which is the implications of causality for decoherence, it's natural to think that quantum causal influences might play a useful role in helping us to pin down the notion of decoherence. Why? Because as I've been arguing, a key tension in Zurek's work is between the mathematically primary role of dynamics and the fact that Zurek doesn't really seem to have a way of thinking about dynamics as conceptually primary. But a very important feature of the concept of causation, both in Pearl's framework and in at least these quantum causal modeling frameworks over here, is that causation is defined purely in terms of dynamics. In the quantum case, purely in terms of the unitary dynamics. And it's going to provide us with a formal language and a set of intuitions that are going to be very valuable when we come to try to pin down the concept of decoherence. But in order to do this, I need to tell you what we actually mean by a quantum causal influence in more precise terms. So let's suppose that we've got some fixed unitary transformation, an operator taking us from a Hilbert space for A to a Hilbert space for B. And this unitary operator represents a dynamical transformation. Now, I'm going to define what it means for an individual operator on A to influence an individual operator on B. And in short, what the definition is going to be is simply noncommutation in the Heisenberg picture. So to lay that out, MA influences MB through U if and only if they do not commute in the Heisenberg picture, where that means that we take NB and we kind of roll it back through the unitary transformation by conjugating it with the inverse of the unitary operator. And we're asking about whether or not that commutes with MA. Okay. Now, you can study the implications of this notion extensively, and it turns out that there's a wide variety of different operational interpretations that are attached to it. But the most obvious one, which many of you might have already spotted, is this one. So supposing that MA and NB are both Hermitian, and by the way, in the following analysis, you could assume that everything's Hermitian and it won't really change any of the analysis. But if MA and NB are both Hermitian, then the generator represented by MA induces a change in the observable represented by this Heisenberg picture version of NB. And this then translates via the unitary to a change in NB itself. So to put it properly operationally, suppose that Alice was acting on HA before U was implemented, and Bob was acting on HB after U was implemented. And Alice is going to implement this MA as a generator, whereas Bob, oh no, I've done it again. So yeah, Alice is going to implement this as a generator, and Bob is going to measure this as an observable. Then the existence of a causal influence is just equivalent to the possibility of Alice signaling to Bob, right? So causation we can understand as a kind of signaling. Okay. Now I'm going to skip over the details here because they're not absolutely essential for us, but I'll just point out that this naturally lifts to a notion of causal influence between entire quantum systems, and it turns out to be equivalent to the notion of causal influence that you'll find in these papers on quantum causal modeling. And again, as I said, these frameworks for quantum causal models, they're serious things. They generalize all these tools that we're used to from Pearl's causal modeling framework. So they actually enable us to do a lot practically when it comes to making inferences between observed data and causal structure, predicting consequences of interventions, and so on. So the fact that this notion of causation is compatible with these quantum causal models is just a further piece of reassurance that it's a sensible definition of causation in the quantum case. Okay. So now I've told you what I mean by a quantum causal influence. We get to the fun bit, which is using it to pin down what I think decoherence really is. We're going to be looking at an interaction, but to begin with, we're not going to be looking at a Hamiltonian interaction. We're going to be looking at a discrete time unitary interaction, right? Represented by an operator from the tensor product of these Hilbert spaces to the tensor product of these ones. The idea here is we're going to begin, and ultimately we're going to transcend this, but we're going to begin by thinking of HA as our kind of system of interest, and HD as our, oh no. Don't know why that happens. Yeah, we're going to begin by thinking of HA as our system of interest and HD as our environment. And what we're going to do is we're going to study really carefully exactly which operators on HA influence operators on HD. We're going to study the exact form that A's influence on D takes. And it's by studying those causal influences that we're going to identify which observables on A are sort of decohered by D, given this unitary interaction. Okay. So, to begin with, I'm defining this algebra of operators A, which are just the local operators that act only on HA and act trivially on HB. And I'm also going to define an algebra of operators for D, but we're going to work in the Heisenberg picture. So you see what I've done is I've rolled back the D algebra through the unitary transformation. So now the algebra is defined on the same Hilbert space that A is defined on. So we can really compare these operators and we can ask if they commute, which is good because, again, causal influence is noncommutation in the Heisenberg picture, right? Okay, so the first question that I want to ask is, what is the complete list of operators on A that do not influence any operator on D? What are the non-influencers? These are the non-influencers. So the intersection of A, obviously, because I'm talking about operators on A, and D prime. So prime here represents the commutant. The commutant, so the commutant of an algebra is the set of all the operators that commute with everything in the algebra. So what this expression tells you is you've got the list of all operators that are on A and commute with all the operators on D. That's the list of non-influencers. But it also has another interpretation. So you might be wondering why I called it A subscript ought. And the reason for that is you can also equivalently define it as the complete list of autonomous operators. What does autonomy mean? Well, I say that MA, like a local operator on A, is autonomous if the unitary maps it to a local operator on C. The intuition here is that the operator just moves from this wire to this wire, and therefore it's just kind of moving on the left side of the diagram, and it evolves autonomously of the right side of the diagram, autonomously of its environment D. Okay, so we got this algebra of non-influencers, or equivalently algebra of autonomous operators. Now, a natural question to ask, whenever you've got an algebra really, is what is the commutant of that algebra? And in particular, I'm interested in the commutant of the algebra within A, right? I want to know what are the operators on A that commute with all of the autonomous operators. And I call this algebra AAC because it turns out that AAC also has a natural conceptual interpretation, and it's in terms of this concept of accessibility. So what do I mean by saying that these operators are accessible? Well, if you think about this definition, then you'll see that these are the operators which have the following property. Any operator on HA that doesn't commute with an accessible operator influences at least one operator on D. So I'll say that again. If your operator on A doesn't commute with an accessible operator, then that operator must influence HD. So why do I call that accessibility? Well, what it means is that any generator on HA that changes an autonomous operator, in the Heisenberg picture, necessarily exerts an influence on HD through the unitary. So what that means is HD notices whenever we make a change to an observable, right? And if you notice whenever a change is made to an observable, that means you have access to it, right? You know about that observable. Good. Okay. So mathematically, we've got these two subalgebras of A, each of which is the commutant of the other. And conceptually, we've got this sort of duality between the concept of autonomy and the concept of accessibility. Now, these notions feel kind of dual to each other because accessibility is about HD knowing about these observables, but autonomy is about these observables evolving independently of HD. Nevertheless, these properties are not mutually exclusive. You have operators that are both autonomous and accessible. Yeah. Could you say that again? Right. So in this whole analysis, we're only interested in what observables on A are decoherent. So I want to take the commutant of the autonomous algebra, but the full commutant would contain operators. Well, it would contain all of the operators that act only on HB. And I'm not interested in them because I'm only interested in HA. So that's why I'm taking the intersection with A. Basically, you can read this whole expression as a kind of commutant. It's the commutant that's defined not in the entire space, but just in the Hilbert space for A. Okay, good. So mathematically, two algebras that are mutually commutant. Conceptually, we've got autonomy and accessibility. They feel kind of dual to each other, but they are logically compatible with each other. You've got operators that are both autonomous and both accessible. And if any of you are really familiar with Zurek's work on decoherence, then that might start to ring bells for you. Because less so in the papers that we already focused on, but certainly in some of his more recent work on decoherence. Zurek often talks about decoherence as a kind of duality. We sort of saw it earlier. On the one hand, the pointer basis, the preferred pointer basis, it remains robust under the dynamical evolution. It doesn't change as a result of the interaction with the environment. And that's a Schrodinger picture idea, right? That's about the quantum state, but it has a similar, it at least feels similar to this notion of autonomy, which is a Heisenberg picture notion. And on the other hand, Zurek emphasizes that although the pointer basis is not being perturbed by the environment, it's nevertheless becoming correlated with the environment. And that idea, at least on an intuitive level, sounds reminiscent of accessibility. We're going to make that connection with Zurek's work much more rigorous later on, but for now, it's a guiding intuition. And using that intuition, we're going to define the decoherent algebra of operators as the intersection of the autonomous and the accessible operators. So to be decoherent is to be both autonomous and accessible at the same time. It's to pull off that balancing act. Okay, now the first encouraging thing about this definition of decoherence that I will note is that it picks out a preferred basis for HA, or more generally, a preferred division into orthogonal subspaces. Because by definition, the decoherent algebra is a commutative algebra, and say we're in finite dimensions, because then it's easier to describe. Any commutative algebra always has this form. It's always sort of generated by taking the span of a PVM, and it's a unique PVM that has that property. Yeah. Interesting. Sometimes Zurek sort of talks a bit like that. Sometimes you get that kind of impression that that's the way he's thinking from his papers. But I wouldn't say so. I mean, so the point of decoherence is to single out preferred and effectively kind of classical degrees of freedom, right? And so you want all the different observables that are marked out by decoherence to commute with each other. If you do this more liberal thing and saying like within these subspaces anything goes, then it's a non-commutative algebra you'll get. Okay, good. So we get this preferred basis, or more generally what a PVM does is it doesn't give you a basis for the, how much time have I got? Okay. Okay, all right. Crap. Okay, well, okay, so we got this preferred basis, and that's encouraging. Let me try to skip through things. Okay, so all of this so far was an analysis of decoherence in applied to discrete time unitary interactions, but we can extend it to Hamiltonians. Essentially, the trick is that we can apply the analysis to every unitary that's generated by the Hamiltonian, and then we take the intersection of all the autonomous algebras that we got before. That gives us the autonomous algebra for the Hamiltonian, and then we can define the decoherent algebra in the same way that we did earlier. And once we've extended our analysis to Hamiltonians, we're able to rigorously make this connection with the way that Zurek thinks about decoherence. Remember that core insight from the 1981 paper was that projectors onto the pointer basis commute with the interaction Hamiltonian, right? So they live in this algebra, is how we would say that. And this returns to your question, right? There are multiple bases satisfying this property, but if we require the pointer observables to be diagonal with respect to all of them, then that means we're restricting to the center of this algebra, which is just the subalgebra that commutes with everything else in the algebra. Oh no. Okay, and the point is that when we're dealing with interaction Hamiltonians, our analysis agrees with this. So although we started looking at decoherence from a different perspective to Zurek, we reached the same conclusions, which confirms that we're doing okay by using the word decoherence to refer to what this is, right? Okay. Now, what I was going to do is I was going to explain how we can then leverage this analysis of decoherence to resolve multiple problems with more traditional accounts of decoherence. And I was going to give you formal details, but I need to shut up, so I'm just going to give you vibes. The idea basically is that our analysis extends to arbitrary circuits of unitary transformations, right? The algebraic structures are nice enough that they scale. And what you're able to do by sort of doing clever things of like combining algebras, you're able to like, within any subset of the set of systems in this circuit, you can do decoherence in this democratic way where there's no preferred system, no preferred environment. Rather, every system is serving as part of the environment for every other system. And in this way, you get 2n preferred PVMs for every system in the bubble. So you democratize decoherence, and that's great because we love democracy, but it's also great because we also like consistent histories, and the PVMs that we derive always form a consistent set of histories. There's a proof sketch, but we're definitely not doing that. And it even it even leads you to a precise realist interpretation of quantum theory. All you have to do is you have to take the formalism that I've very briefly described to you literally, and you're essentially saying that what's going on in the universe is that there's a unitary circuit, and relative to every bubble, so that was every subset of the systems in the circuit, one of these emergent causal decohistories will happen with a probability given by the probability rule that I didn't derive for you just now. And yeah, that's it. That's the interpretation. It's a precise realist interpretation that's very different to the ones that you'll be familiar with, like Bohm theory or Everett or GRW, because the state is playing no fundamental role in this interpretation. And this is the core point about this interpretation, that the state plays no fundamental role. We have a unitary circuit, and we sort of think of that as dynamics, but not in the conventional way. We don't think of the dynamics as a rule for acting on states. It's a thing in and of itself, right? In the same way that you're used to thinking that states just exist, for us, dynamics just exist. And we're able to rigorously make sense of that because we've got this formalism for deriving kinematics out of the dynamics, right? And so I started this talk by arguing that what we needed is a dynamics first view of decoherence. In the end, what we found is that by giving a dynamics first view of decoherence in terms of quantum causal influences, we have not only been able to understand decoherence in a dynamical way, but we've been led to a dynamics first interpretation of quantum theory itself. That's what we've seen, albeit quite in a rushed manner towards the end. Okay, so sorry for taking so long. I will stop there and be happy to talk to anyone more.
Thank you. So too bad you had to at the end, because at the beginning of your talk, when you advertised a new realist interpretation,
Yeah,
that's what I was looking for.
yeah,
Looking forward to, I mean. But of course, I was too quick. I didn't really follow. But
yeah.
but still, I have a few questions about it. One is that I understand that it's not state-based, but
Yeah.
based on the Heisenberg picture.
Yes.
And so my two questions really are, is it local, including separable? The answer is yes, thank you.
Well, sorry, I was.
Oh, okay.
It's a bit complicated, but yeah, go on.
Well, the other question is how is it then? You said it's different from what we might have heard of, including Everett, but how is it different from the Deutsch-Hayden interpretation, which is based on what call?
Yeah.
And where what evolves are not states but observables. There's a difference between tracking evolution dynamics. Is that a different thing?
Yeah. Really good questions. Okay, so the first question was about is this a local inseparable theory, and then the second question is how exactly would we characterize the difference between this Deutsch-Hayden interpretation? Okay, so on the locality issue, as you already identified in your question, there's multiple different notions of locality you can talk about. One notion of locality would be, are there non-local causal influences? The answer is no, there aren't.
That's not locality. Yeah, that's no actual distance.
Okay, fine.
So that's no observable actual distance.
Yeah. Yeah. Okay. In terms of the separability part of the question, it's definitely not non-separable. But there's a part of me that doesn't want to say that it's separable, because to me the whole categorization of theories into separable and non-separable is something that only obviously makes sense on a state first view of physics, right? So fundamentally what there is just a unitary circuit, which isn't a state. There's nothing, I don't think there's anything non-separable about that unitary circuit. Maybe I'd have to think about it more. But yeah, really, it's not, yeah, I wouldn't want to advertise this theory as saying, yeah, it's a separable theory, because that would suggest that states are playing a primary role, which they are not. Okay, and I guess, yeah, that does segue into the other question about what is the relationship, or what is the difference with the Deutsch-Hayden interpretation Deutsch-Hayden-Everett interpretation of quantum theory. Okay. There's definitely a close connection, and I believe that the mathematical formalism that we've developed here is relevant, could be useful for people who are working on the Deutsch-Hayden interpretation. Because, you know, at least assuming that even on the Deutsch-Hayden interpretation, the story of the Everett interpretation is that these different branches are emerging via decoherence. Here, you can think of our formalism as just a way of treating decoherence in the Heisenberg picture. So it seems to be an apt formalism if what you want to do is tell that story of branching. But to answer the question more specifically, if what we're contrasting is this particular interpretation of the formalism with the Deutsch-Hayden approach, the most fundamental difference is that this is not a branching multiverse theory. So the Deutsch-Hayden, well, maybe you could argue that Deutsch-Hayden is not branching multiverse in the same way as traditional Everett interpretation is. It's not at all.
I don't know.
Go ahead.
Okay, I'd love to talk to you more about.
I mean, it is influenced, of course, by Everett.
Yeah.
But the thing is a version is something that could hardly be more non-local.
Yeah, sure. But it was okay. Maybe we can talk about this more, and you might be able to correct some confusions I've got. But my understanding was that although it's not branching multiverse in the sense that there's a quantum state of the universe and it's the quantum state that's branching, there is still branching that takes place in terms of those descriptors, was my understanding. My understanding was that you're still talking about a kind of state on this approach, but your states are not the quantum state vector. It's rather these descriptors, and there's an argument that this is better because of separability, et cetera. On this approach, right? Okay, maybe here's the best way to get to the core of it. There is an alternative Everettian interpretation of this formalism, right? Where you say that whenever you get one of these history sets emerging from decoherence within a bubble, you do the Everettian thing of saying all of these histories happen, right? Every history corresponds to a different branch of the universe. They're all equally real. That's not what we're doing over here. What we're doing over here is we are postulating that only one history happens relative to every bubble. And what history is going to happen? Well, it's not predetermined by anything. It's genuinely stochastic. And we've got the probabilities for calculating the chance of a given history to occur. And actually, and of course, you know, different people will have different opinions on this depending on what you think about probability theory and derivations of the Born rule. But to me, that's actually the main selling point of this interpretation as contrasted with the Everett interpretation, is that there's a lot in common, right? Like just with the Everett interpretation, this is an interpretation, a realist interpretation of unitary quantum mechanics without additional variables, without collapses, anything like that. But unlike the Everett interpretation, which often, or maybe always, requires an exotic interpretation of probabilities as not corresponding to relative frequencies in the way that you might naively expect, at least, we don't require such an exotic interpretation of probability here. It's no more exotic than is required by any interpretation that is stochastic.
Obviously, this is generating very passionate discussion, but I'd like to, we're past 2 now. I'd like to release people. Nick, let us thank him. And by the way, I want to say that he's around. So any one of you wishing to explore and ask further questions are welcome to do so. So let's thank him.
Thank you.